Now, without wasting time, I'll introduce the professor for the next session. The next session is on processing and manufacturing and properties of high temperature titanium alloys. Now we have with us Dr. Amit Bhatachary, scientist G from and group head of Titanium Alloy Group, DMRL, Hyderabad. A dynamic career spanning more than 32 years in the field of metallurgical engineering, consisting of industrial metallurgy, teaching, and R&D in various organizations, started in silicon steel in steel mill of Rourkela steel plant in the production of CRGO and CRNO electrical steels. And then moved to Asia Brown Boveri, Vadodara, at their corporate R&D center, where he was involved in failure analysis and vendor development, and subsequently taught the engineering students of defense forces at College of Engineering, College of Military Engineering, Pune, and DRDO posting. Since May 1997, he has been associated with the Defense Metallurgical Research Laboratory, DMRL, Hyderabad, India, and is involved in research and development of titanium alloys, and is recipient of several awards. He also served as a postdoctoral fellow at the Ohio State University, Columbus, USA, where he worked on a Federal Aviation Administration funded project and looked at the effect of microtexture on dwell fatigue of near alpha titanium alloys. He also taught courses in IIT Kanpur as an adjunct faculty for 1 year. Sir obtained a bachelor's degree, master's degree, and PhD from Department of Materials and Metallurgy Engineering, IIT Kanpur, and postdoctoral research fellow at the Materials Science and Engineering Department of the Ohio State University, USA. He was the leader of several aeronautical development agency Bangalore funded projects. Few of them are indigenous development of high strength beta aluminium for structural weight reduction in Tejas, indigenous development of high temperature beta aluminium alloy, cold rolled steels, cold rolled sheets. And he is presently project director of indigenous development of titanium alloys and associate manufacturing technologies for AMCA. He is also involved as a titanium expert member in several projects like that of Navy and titanium armor, etc. He was recipient of several awards, which includes Agni Award 2007, which is a team award for contributions in development of indigenous development technology for self-reliance. And 2 best presentation awards in ATM and IAM. And Engineer of the Year Award 2015 by Institute of Engineers, Telangana Government, and a DRDO Laboratory Award, a Scientist of the Year in 2015, and also Fellow of IAM. He has published around 70 papers and reports in national and international journals, and 2 IAM book chapters on aeronautical materials. With this, he also a reviewer of several international journals like Journal of Material Transactions, MSc, Journal of Alloys and Compounds, magnetic letters, transactions and IAMs, etc. And he is also member of several review boards, Geeta, ARNDB, DRDO, GTMAP, which come and DRDO, etc. Thank you, sir. Thank you, sir, once again, and welcome you, sir. Sir, now the session is open to you, sir. Please, you can start the session.
Yeah, thank you, ma'am, for your kind introduction, and thank you, Padmalata, ma'am, for having me here and giving me an opportunity to talk to I think there are faculty members who are there. So I will start, and I congratulate all the organizers for maintaining time, and also I can one of the times that I can start in time. So I will begin my talk, and I will be talking about this processing manufacturing properties of high temperature titanium alloys and high strength beta titanium alloys for aerospace applications. I hope you all are able to hear me, right?
Yes, sir, we can hear
Yes,
you
sir.
clearly.
Yeah, sure. And you are seeing my slide. Okay. Now, before I start, I have to acknowledge Director DMRL, Dr. Madhusudan Reddy, Dr. Kamath, who's our DG NSM, Professor J.C. Williams, who's some of the work that I'm showing, Professor D. Banerjee, who introduced me to titanium, Dr. Gogia, and Dr. Nandi, who are my colleagues in DMRL in the titanium group, and also members of the titanium alloy group and others. So this is how I will go about my talk. Firstly, give a brief introduction about classification, melting, corrosion, etc. Then also talk about alpha alloys, and then come on to alpha plus beta alloys. Although the focus will be high temperature titanium alloys, in which I'll be talking about near alpha conventional high temperature titanium alloys, and also the intermetallic gamma titanium aluminides, which are now point of interest, and then talk about high strength titanium alloys, which are for structural aircraft application. In that, I'll be talking about beta alloys. And finally, if I have time, I can manage time, then I will also briefly introduce titanium biomedical alloys, because that is also one field of research which is coming up. So as far as titanium goes, it has two principal virtues. One is high strength to weight ratio and good corrosion resistance. And that is the reason you find applications in lot of industries and applications like aerospace. In the aerospace, you have application in airframes as well as engine components. And then as far as due to its good corrosion resistance, it finds usage in marine, chemical, and biomedical applications. And then there are certain other niche applications which are very, very not very common, but still they are there. And these are the industries like aerospace, medical, industrial, and certain specialist industries also there, which is coming up, like body jewelry, marine, bicycle, and then also sports equipment. And as far as the percentage usage goes, non-aerospace, it's 47% of the total production, and in the aerospace, it is 53% of the total titanium alloys. Now, as far as titanium goes, it is basically extracted from its oxide, which is available a lot in the Kerala beach sands, and this titanium oxide is very stable. It as mineral, it occurs as rutile and ilmenite. I will not go into the process metallurgy because that is not the point of talk now, but just wanted to introduce. And because of its high chemical reactivity and the higher melting point, it took some time to isolate pure titanium, and it is still now industrially extracted by the Kroll's process. That is, TiO2 is converted to TiCl4, and then it is reduced with magnesium. And this technology in India has been again done by DMRL, and then now a plant has been set up in Chavra, Kerala, of 500 tons per annum, where titanium sponge is being produced. Now, coming back to the titanium alloys, here I'm just showing you how the classification is done. Now, the alloying elements are basically divided into two categories: the alpha stabilizers and the beta stabilizers. Now, what do alpha stabilizers look like? These are these elements, and the common ones are one of the main important one is aluminium, oxygen, and nitrogen, and then there are rest are these which are less used. And if you see this part of the phase diagram, what if you add alpha stabilizer, what it does is it stabilizes the alpha phase field and increases this temperature line, which is called the beta transverse temperature line. And then coming to beta stabilizers, there are two kinds of beta stabilizers. Beta isomorphous, which are these elements: vanadium, moly, niobium, tantalum, tungsten, and then beta eutectoid stabilizer like iron, chromium, nickel, and in the gaseous elements, hydrogen is the is the element which stabilizes the beta phase. And the beta iso, what these beta stabilizers do, they basically stabilize the beta region, and so they bring down this beta transverse temperature line. This is for isomorphous. This is for the eutectoid stabilization. Then there are certain elements which have no effect on this beta transverse temperature lines, but they are added. I will show you why they are added, like tin and zirconium. So these are called neutral elements. That is, they don't have much effect on either alpha or beta. Now here I'm showing you this is basically a pseudo-binary phase diagram. That is a imaginary diagram which has been drawn. Here on the y-axis you have temperature. On the x-axis you have beta stabilizer concentration. Now what is beta stabilizer concentration? It is basically calculated by this empirical formula, which is known as Molly equivalent, and it is a measure of beta phase stability. So higher this number, the more the alloy is beta stabilizer. So you can see here all the beta stabilizing elements along with their multiplying factors have been put in. And so you can put in whichever elements you are there in the alloys, multiply by which and get a number. So that is what is plotted here, beta stabilizer concentration. And then there is another one which is known as aluminium equivalent. That is a measure of alpha phase stability. And in these, there are only a few elements. Aluminium, as you can see, is one of the main stabilizers. Tin and zirconium, which are neutral, come in. And these are the oxygen, carbon, and nitrogen are also the alpha stabilizers. Now, if you look at this pseudo-binary phase diagram, here you have the single phase alpha region. Then you have the alpha plus beta region in between. And then above this temperature line, you have the beta phase. So above this temperature line is what you get is beta phase, which is, I will show you the crystal structure. Now, this is a very important temperature as far as titanium alloy goes, and this is called a beta transverse line. And in titanium alloys also, you can see this line, the dotted line, which is the martensite start line. So in titanium alloys also, you have martensite formation, but it is not as strengthening as in steels. So as far as strengthening goes, it is of less important, but it does other things, refines the structure, and also that is why. But nonetheless, it exists. The martensite forms. Now, so here I am showing you the classification of the conventional titanium alloys. That is, on the extreme left-hand side, you have a single phase region, which is the region of alpha alloys. I will talk about these slightly detailed, not too much. Then you have in between these two lines is what you have alpha plus beta alloys. And I will show you the examples also. Now, if you see here, this is room temperature. So wherever this martensitic start line crosses the room temperature, that is where you have this alpha plus beta alloy category, because that means alpha plus beta alloy, if you quench from above the beta transverse, above room temperature, you are going to form martensite. Then comes the category of beta alloys, mostly metastable beta alloys, where if you have the alloy and do a beta heat treatment, that is, you take it up, heat it up here, and then cool it, then fast enough, then you should be able to retain the beta phase. It does not decompose. That is what is the classification. Then you can age to attain high strength. So that is the, in brief, classification of conventional titanium alloys. I will talk about intermetallics briefly later on. And then you have the stable beta alloys, which are less used, which is very, very higher amount of beta stabilizer content, but they are there. So here again, I'm showing you the examples of certain commercial alloys. All the alpha alloys like 5Al, 2.5 tin, and then there is also commercial purity titanium, which is an alpha alloy. Then there are other examples of alpha alloys in this category, alpha plus beta alloys, which you can see. I will show you again. One of the important alloys that I should point out is Ti6 aluminium 4 vanadium, which is an alpha beta alloys, and the around 50% of the world titanium production is of this alloy, because this is medium temperature capable, good strength alloy, and it is used widely in many of the places. Then you have the metastable beta alloy, 10 titanium, 10 vanadium, 2 iron, 3 aluminium. Then you have the other alloys also. Now here, what I'm showing you is the sorry, we go. Yeah, on the red part of the bar shows the aluminium equivalent, which formula I had given. That is, it tells you how much the alloy is alpha stabilized, and the light blue color bar shows you how much it is beta stabilized. So on the top side, you have the near alpha alloys, which is a subcategory of alpha plus beta alloys. This category we'll be talking about in detail. And this is part of the alpha plus beta alloy. And you can see you have higher aluminium equivalent and a very less amount of beta phase on the near alpha alloys. And then as you go down, the amount of alpha stabilization decreases and beta stabilization increases. The other thing, this is the beta transist temperatures indicated here, or several commercial alloys. You can see as you come down for near alpha alloys to beta alloys, the beta transist temperature is also roughly going down. So now, most of the time in titanium, we are talking about, especially in conventional titanium alloys, we are talking about these two microstructure. That is, we are heating either to the beta region or BCC region. This is what looks like. This is a BCC crystal structure, and this is the closed packed plane which is there. And then when you talk about alpha, we are talking about the HCP crystal structure, which looks like this. And here I am showing you the slip planes. This is the basal plane. This is called the prismatic plane. These are called pyramidal planes, and the names and the directions are indicated. I will not go into too much of details about this. So the slip or deformation happens on this and this very easily, and slightly more difficult on these pyramidal slip planes. So here again, I am showing you the same both BCC structure and the HCP structure, and again indicating you sorry. Hello. Here also I'm showing both the structures, and whenever you transform beta to alpha, that is, you cool down after heating to beta phase, what is done is in this there is a Burgess orientation relationship which is followed. That is, the close packed plane of this matches onto the close packed plane of this. That is what is shown here, the hexagonal basal close packed plane, and this plane, which is this. And you can see there is only one direction in which it matches perfectly. Other direction, there is a slight mismatch. So what happens is 001 of alpha, which is this basal plane, or 002 matches onto the 110 of beta, and the close pack direction, one of the close pack directions, to 1 bar 1 bar 0 of this matches onto this direction, one of the diagonals, this or this. So what happens is there are 6 110 planes, and in each this 110 plane, there are two directions, close pack direction, 111 types. So this gives 12 variants of the alpha phase when beta is transforming to alpha. So that is why whenever you look at the microstructures of titanium alloys, you will see a very geometric pattern. And that is the reason for this Burgess orientation relationship is the reason for that. And that there are other, in steels also you get these kinds of orientation relationship like Kuzmos, Sachs and others. So this is very important in titanium alloys. That is why I'm talking about it. And mechanical, why we are talking about this is because mechanical properties are dependent on it. The microstructure affects the mechanical properties, okay, as you will see slowly. sorry. Now I'll just introduce some of the heat treatments that we know. First is the homogenization heat treatment, which is normally done to all the solidified ingots. It is heated in the high up in the beta phase regime, quite high, around 1100, mostly higher than 1100 to 1200, 1250 or so, to basically homogenize it. That is to basically prepare it for forging and all. And if there is any chemical inhomogeneity, then it also evens out. Time and temperature are decided depending on the alloy and other things. Then as far as solution treatments are concerned, there are kind of two solution treatment. One is beta solution treatment, which is normally carried out in the lower beta phase regime, but in the beta phase regime. And then there is also alpha plus beta solution treatment, which is carried out in this alpha plus beta. So beta solution treatment is carried out here, and alpha plus beta solution treatment is carried out here. Then you have aging, which is again carried out in the alpha plus beta regime, but lower down in temperature. Okay, roughly in this regime, 500 and below. It can be go up to 600, but it is normally lower temperatures. Then you have alpha solution treatment being carried out in alpha alloys, which is here. Then most of the time, the stress relieving of titanium alloys is carried out in the temperature regime of 400 to 700 degree centigrade. And there is also a term called mill annealing. Now, what is mill annealing? Mill annealing is annealing in the mill furnace. That is the furnace that you are using for deformation, for wrought processing of the alloy. You give some annealing operation, let's say after deformation for roughly 1 hour or so, not much. So some residual stresses and deformation might remain after mill annealing. And this is a standard term which you will see in many supplying companies and all. So that is why I'm trying to introduce you all to the, yeah. Yes, any okay. The other important thing which you all should know is titanium alloys, the globalization of alpha. You see, as I told you, alpha occurs, this is beta and this is alpha. So they occur as needles, or depending on the cooling rate, they will be thicker or thinner. Now, this is a very, very important treatment. Suppose you want to convert alpha from the lamellar structure to a globular structure, it cannot be done just by heat treatment as in steel. Normally, it occurs as laths. It is like quadratic laths in steel. You have alpha and beta, very thin beta around. So what you have to do is do a deformation in the alpha plus beta temperature regime when you formation of slip bands are there. And then what it does, the beta phase pierces the alpha phase because of the surface tension effects. And then when you heat it, grains, the elongated grains of alpha become rounded. And once you do solution treatment in the alpha plus beta regime, you can give globular alpha. It is required. I will show you why it is required. And this is one of the examples where beta is entering and breaking off the lamellar alpha. Now here I'm just showing you the different microstructures that you get before I go on to the detail. So this is a pseudobinary phase diagram and taken an alpha beta alloy. And if you heat and cool, this is air cooled and this is water quenched. Now, if you water quench, you get a very fine lath-like structure. This might be martensite, depending on the cooling rate. And this can be alpha or martensite. Titanium alloys is very difficult to make out whether, if you do TM and all, you might be able to make out which is martensite, which is alpha. Okay, they both have crystal structure, very slight difference in the lattice parameters. Then if you deform in the alpha plus region and heat it, you start getting cool it, you get again globular alpha, and the transform beta region can be very fine transform beta, like in the top, and then you get globular alpha whenever you do deformation and heat it. So heat treatment in this regime. So this is what you get. Again, now coming to the, this is a Russian alloy. I'm just showing, it is a commercial purity titanium. Commercial purity titanium also has strength similar to many aluminium alloys. So that is why they are used. And so you get a single phase structure, which is, you can see the grains. This is one of the alloys. This is commercial purity. Then there is another alloy, which is called a half alloy. Half alloy composition wise is half the composition of Ti6Al 4V, and you can see very fine beta around the boundary. Rest is all alpha. This is a SEM picture. Now here again, Ti6Al 4V, when you beta heat treat, cool from the beta region, and you cool it, you get this kind of colony structure. You can see different colonies of alpha, and you can see the geometric pattern. This bright thin layer is beta, and in between darker regions are alpha. And what you can see, you also can see grain boundary alpha formation, because this is a high energy region, grain boundaries, and alpha first precipitates on these grain boundaries, and that deteriorates the mechanical properties. So you have to take care of it. Now, if you give deformation to this material, beta treated material in the alpha plus beta regime, and then cool very slowly, what you get is an equiax structure. You can see alpha, dark color alpha and beta lining, continuous beta lining the boundaries. So this kind of microstructure is very good for superplastic forming application or forming application. Okay, but you see deformation and rot processing can change this structure to this structure. Then there is also something known as bimodal structure. This is an example of a IMI 834. It's a high temperature titanium alloy, which is used in aero engines for in the compressors, etc. So here you can see why it is called bimodal is because you have got this primary alpha and transform beta, and the grain sizes, as you can see, have reduced quite a lot from this to this. This kind of microstructure is very desirable if you want good fatigue and all. If you cool faster, you get a slightly finer microstructure. You get finer beta and also finer grain size, and also lathe size is finer. So this is also a bimodal microstructure. Okay, now I will just briefly talk about how melting is done, because some of you might not know. So that is why I thought I will just go through the basics and then go on to the main topic. Now, titanium picks up oxygen and nitrogen, etc. that is there in the, so it has to be melted in vacuum. So what you do is you have a melt it in vacuum arc remelting furnace. What you do is you make a electrode, and then there is a water cooled stringer rod to which, or an electrode which you attach, and then you have a water cooled copper crucible, water around, and there is a stirring coil around. And so you arc between the electrode and the bottom of the crucible and start the melting, and you keep pushing the electrode down. So this is what you have, and the vacuum is applied through vacuum pumps. So this is again a schematic. You have this vacuum pump, and then you have this copper crucible in which it melts and solidifies part by part. Okay. So this is a picture of an industrial scale furnace, which is, most of it is underground. It can be underground and also above the ground, both ways. So this is one of the first pictures of the titanium sponge produced by DMRL in DMRL, and so that is, I just wanted to show you. And as I told you, there is a lot of raw material in our Kerala beach sands, and so this was the cake that was made in DMRL, first cake which was produced in DMRL. There's a big retort which is there. Now, as far as titanium melting goes, there are basically, it can be carried out in non-consumable mode or consumable mode. In the consumable mode, you melt the electrode itself, and you can melt larger quantity, right from 5 kg charge to any. Whereas non-consumable melting, you can melt smaller quantities, and there is a thoriated tungsten electrode, and arcing is between the material and the thoriated tungsten electrode, because the electrode is not melting. So that is why it is called a non-consumable melting. And here I'm just showing you how the charge calculation is done. Suppose I want to melt titanium 5, aluminum 5, vanadium 5, moly 3, chromium. These are all weight percentages. This is a 5553 alloy. So you take titanium sponge 41. Suppose you want to make a 5 kg electrode. You have this much of titanium sponge and this much. Now you have to add moly and you have to add vanadium. Now the moly and vanadium both have higher melting points and higher density as compared to titanium. So they tend to segregate. So that is why they are added in forms of master alloys, aluminium based master alloys. Okay, so these are all imported. India does not make these aluminium based master alloys. Only iron based master alloys, which are very much required by steel industry, is melted and processed. So you add these master alloys, that brings down the melting point as well as the density, so the mixing is proper, and then you add aluminium shots and chromium pellets. So this is the typical charge for, let's say, if I want to melt a Ti-5553 alloy. So you can multiply depending on the Hello, I hope I'm audible. Hello.
Yes, sir, we can hear you.
Yeah, because somebody muted everybody, so I just wanted to check out. Yeah, so this is a typical charge, as I said, depending on the weight of the electrode, you can calculate and then melt the electrode. Okay. Yeah, here I'm just showing you the industrial scale electrodes and melt. On the top left hand side, you can see a compact which has been made. This is a 172 kg compact of an alloy that has been made and welded together. So this forms an electrode, and this is a melted melted ingot. So you can see it's a 650 mm dia ingot, 2.8 ton ingot. So this is the industrial scale melting, and we can do in lab scale we can do 10 kg, 20 kg or whatever you want. And then this is a button which is melted in non-consumable electrode process, and also this pancake. This is around 100 mm dia and 7 to 8 mm in thickness. The other important thing about titanium is it has got a very good corrosion resistance because it exists in the noble end of the galvanic. This is a galvanic series in seawater, and titanium exists towards the noble end. It just like aluminium, it forms a oxide layer which protects. Although this oxide layer is not as tenacious as aluminium, but still it protects. So it has got very good corrosion resistance. That is why it is used in a lot of marine applications and also chemical industries. Now, so as I told, the thin protective layer of TiO2 on the surface, which forms protects it, but it is good in oxidizing environments, that is in chlorides, hypochlorite, sulfates, and chromic acid solutions, but is not as good in reducing environment like all the sulfuric acid, hydrochloric acid, phosphoric acids, etc. And in order to improve it, you can do palladium additions, which increases the corrosion resistance. Then titanium and titanium alloys is slightly different as compared to steel. Because it is melted in vacuum and the materials are very pure, there are no inclusions. So there is no pitting corrosion that happens. But the local chemistry changes can dominate the corrosion behavior, and you can have crevice corrosion. I will just briefly show you that. And CP, commercial purity titanium, with additions like palladium, etc., and all compete very well with nickel based alloys and also stainless steel, etc., as far as density corrected strength is concerned. This but the titanium alloys are quite prone to crevice corrosion. That is all the alloys that have a thin protective layer. That is when you put two surfaces together in close contact, and let's say you have an environment here, it's a liquid, and then a cell can form and the corrosion can start, because this cell does break down the film, and that creates this is called a crevice corrosion. So titanium is prone to crevice corrosion, but other kinds of corrosion are less in titanium. So you don't have rusting of titanium and all as in steel or iron. Now coming to alpha titanium alloys class. Now these have a moderate strength and good fabricability because they are single phase and has got very good corrosion resistance. Now there are certain modifications which have been done, which I already pointed out, like palladium bearing alloys are good for in reducing environment and all. So there are usages like for making electrodes in what is electrolytic bath, etc., or electrowinning of some materials. These titanium electrodes are used. Now, as far as the grades go, there are about 16 grades of commercial purity titanium and alpha titanium alloys, US and other industrial countries. These alloys, the very fact these are single phase alloys, they are non-heat treatable. Okay, that is, you don't gain in strength by heat treating. So that is why they are called non-heat. But certainly you can do a stress relieving and all. This commercial purity titanium and alpha titanium alloys approximately comprises of 1/3 of the total titanium market today. And here I'm just showing you the different grades of CP titanium and the alpha titanium alloys. You can see grade 1, grade 2. What is the difference is the amount of oxygen. Oxygen is a alpha stabilizer and also a strengthener. And here I'm showing you the yield strength, 0.2% yield strength. And as you see, as the oxygen content is going up, the yield strength is also going up. And then these modified alloys with palladium and ruthenium and all, and these are the yield strength. And then there is this half alloy which I was talking about, is titanium 3 aluminum 2.5 vanadium. This is also can be categorized as alpha alloys or alpha plus beta alloys, but normally because it is non-heat treatable and its strength is slightly higher. As soon as you alloy it with other elements, you can see the yield strength is. This is widely used in aircraft tubing and all. I will show you. This is how the alpha titanium alloys are processed. Plus, it is homogenized in the high up in the alpha regime only, and then deformed in the alpha regime, and then recrystallization again in the alpha regime, slightly higher than the deformation temperature. That is how these alpha alloys are processed. It is completely processed in the alpha regime. Here is an example of microstructure. This is of a alloy 5-walled tin, and then you can see there is very slight amount of beta which controls the grain size, and there you have iron for stabilization of the beta phase. Otherwise, it's a single phase alloy. This is one of the usages, making this heat exchangers like this, tube heat exchangers, which can be made. These can be formed into tubes very easily, and you can make heat exchangers. Here I'm showing you the usage of this half alloy tube. Again, the microstructure I'm showing here, you can see bright beta and all single phase alpha. This is used for hydraulic oil. This for usage in aircraft, hydraulic oil carrier tubes. You can see there are miles and miles of these tubes in an aircraft, and various thicknesses and dias are used, and indigenous. This has been produced indigenously also with in Midhani and NSC, which makes tubes, and this is how it is processed. Half alloy bars are melted, then it is pilot board, hot extruded, series of cold pilgering, annealing, pickling, and then qualification tests are done. Just showing you the tubes which are there of various dia and thicknesses. Now, I'm not going into too much of detail of alpha alloys. Then comes the bigger category of alpha plus beta alloys. Here are some of the examples of the alpha plus beta alloys. This alloys, for example, Ti6Al4V. There are two grades. One is the normal grade, which has got higher amount of oxygen, and then a grade which is called the 6,4 ELI, which has got lower amount of oxygen, 1300 ppm of oxygen. This is for formability and cryogenic applications. Then this is then comes the category of high temperature titanium alloys, which are near alpha alloys. 6242 is one of the high temperature titanium alloys that Americans use. And we have, for a Kaveri engine program, we have indigenized this alloy. This is a slightly later version alloy and a slightly more complex alloy. And this has also got higher temperature capability as compared to this. This can be used up to maximum 500, 525 degrees centigrade. This can go up to maximum 550 to 600 degrees centigrade temperature. These are older generation alloys which are there. 811, IMI 685, which was used in older engines, etc. This is the cut-up of a jet aero engine. The front portion can be of titanium, Ti64 mainly, or it can be a composite. Then comes the low pressure compressor or booster. Then comes the high pressure compressor. So all these can be titanium. Front portion of the compressor section can be titanium alloys, high temperature titanium alloy. Front portion are Ti64 and all, which has got lower temperature capability. Then you have the turbine section. Nowadays, I will talk about briefly about aluminites. They come in here. So this can replace aluminite, which are intermetallics, can replace nickel-based superalloy. Otherwise, these are nickel-based superalloys. Then there are certain alloys which can be used for engine tail plugs also. How is this alpha plus beta alloys produced? These are processed. This is just 1 second. Let me check if I can hide this. Okay. The ingot, as I told you, is heated up high in the beta phase regime. So that is called homogenization. Then you can cool at different rate. Then deformation first is carried out in the beta and then in alpha plus beta regime if you want a bimodal kind of structure. Otherwise, if you want a beta treated structure, you can just do deformation here and then annealing or recrystallization here, you get a beta treated structure. But if you want a bimodal structure and want to refine the grain size, you deform in the alpha plus beta regime and then carry out recrystallization and annealing is again in the alpha plus beta regime, and then final aging or annealing much lower down to get higher strengths. So here are again the same microstructure. I'm just this is a beta treated structure. It has got big beta grains because the diffusivity in beta or BCC is higher, so you get large grains. And in beta treated structure, whereas equiax or bimodal, you can see the you get much finer grain size. So for like fatigue kind of application, this kind of microstructure is much better, and this kind of equiax microstructure is good for formability applications. I'm just showing you here the tensile ductility, that is percentage elongation versus yield strength. Equiax microstructure is better if you that is at a comparable tensile at yield strength. The equiax structure has got higher ductility as compared to lamellar microstructure. Lamellar microstructure normally has lower ductility, but lamellar microstructures are better for creep kind of applications. Then as far as fracture toughness versus yield strength goes, the lamellar microstructure is better off for fracture toughness, and equiax microstructure fracture toughness is slightly compromised. Now coming to near alpha high temperature titanium alloys, because these exist toward the left hand side of the alpha plus beta phase diagram. Now, what is the design philosophy for high temperature? We are mainly looking for creep and oxidation resistance. So what you have to do is basically limit the beta phase volume fraction, because as I told you, beta phase, because it is BCC, the diffusivities are higher. So you have worser creep properties. So you have to decrease the beta phase content. So it is normally kept less than 10 volume percent. So that is why you have to have lower beta stabilizer content. Then how do you strengthen? You add this neutral element, tin and zirconium. Tin combines with aluminium, and it can also precipitate alpha 2, which is ordered Ti3Al structure, which increases the strength, high temperature strength and all. So it is good for that also. So as I told you, you replace the higher diffusivity beta stabilizer. You have to add certain amount of beta stabilizer that you add. Instead of using vanadium, you can use moly or niobium, which are has higher melting point and diffusivities are lower. So that is why you will see in high temperature titanium alloys, you will have more of moly and niobium. Then other thing that you have to be careful about is very low amounts of iron and nickel can affect your creep properties, because iron and nickel enhances titanium self diffusion, and very, very small amounts of it causes anomalous diffusion, and that is why the creep properties get compromised. So you have to be very careful. So I will show you this effect. And normally in high temperature titanium alloys, silicon is added because you precipitate silicon, as I show you, and this blocks slip transfer and also reduces grain boundary shining. So these are good for creep kind of application, but you cannot put in a lot of amount of silicon because it also forms brittle, continuous brittle films, which so it renders the alloy brittle. So you have to be careful. So normally it is kept below 0.5% and most often around 0.2, 0.3 or so. And then there are other heat treatment which can also mitigate that. We will not talk about here in this lecture. So now, as compared to the alpha plus beta alloys, you see how these alloys are slightly more complex, high temperature near alpha titanium alloys. There are other solvers that have come in. That is silicide solvers, which is in the alpha plus beta, and there is also Ti3Al solvers. Ti3Al you want if you want high temperature, that is the ordered alpha. Now, because these are intermetallic, so you have to be careful where you deform and heat treat and all. So the first step is the homogenization. This I need not talk about. I have already talked about it high up in the beta regime. And then if you want a bimodal structure, why you want a bimodal structure, I will tell shortly show you. You do alpha beta deformation, and that is above silicide solvers. It cannot be very low. Then why higher? Because then if you have already formed silicide, then the material will start cracking. Okay, because silicide is brittle. And then you anneal it or recrystallize it slightly higher than the deformation temperature. And then final annealing and aging is below all the transistors. So finally, you precipitate out all the Ti3Al as well as silicide to improve the properties. This is how high temperature titanium alloys, near alpha titanium alloys are processed. Now, why we add silicon? You can see this is a TM picture. This is alpha lath and beta, which is this dark gray structure. This is very discontinuous. It is not a continuous lath. You can see because the beta volume fraction is low. So what you do is when you put in silicon, it forms silicide and it precipitates around the beta boundaries and at the interfaces of alpha and beta laths. This is alpha, this is beta, discontinuous. So the slip transfer cannot take place from alpha to, that is, you restrict the deformation, and that is what improves the creep properties. It also prevents grain boundary sliding, which is one of the phenomena that happens during creep, and that improves the creep property. That is why in most of the high temperature titanium alloys, you will have silicon as one of the additions. It improves the high temperature creep property. Here I am showing you a very, very small, very, very large effect of very, very small amounts of iron and nickel. You can see this IMI 834 was melted in DMRL with master alloy and other combination, which had got iron and nickel in this range in the final composition, whereas the imported alloy had got lower amounts of iron and nickel. You can see the very, very small amounts this is 65 ppm, this is only 20 ppm, whereas this is 233 ppm parts per million, and this is 90 ppm. And you see the creep properties were measured, and at 150 MPa as well as 200 MPa of load level at temperature of 873 degree Kelvin, that is around 600 degrees centigrade. And you can see this is Pyramidal 834, which has got lower amount of iron and nickel. As compared to that, this has got higher amount of iron and nickel. And you can see same stress level and temperature, jump in creep property. That is, it is deteriorating as far as creep resistance is concerned. This also jumping up to, so you are having much higher creep strains. Okay, so so you have to be very careful about iron and nickel in high temperature titanium alloys. Now, here there are two microstructures, bimodal and lamellar, where creep strain has been plotted. So here I'm showing you the bimodal microstructure has got worse creep as compared to lamellar structure. So lamellar structure is good for creep. But as far as fatigue is concerned, you can see here we are plotting fatigue curve, and this is a property value, just hypothetical curves, and these are curve, and this is a beta transverse line. So as you cross the beta transverse, you get a lamellar structure. So the creep properties are improving as you go towards the lamellar structure, whereas fatigue property deteriorate as you cross this. So it is, fatigue property is much better if you have a bimodal kind of structure. Now, for applications like blades and all, where you have higher temperature and also rotating, so you have to have good creep, combination of creep and fatigue. So that is why a bimodal microstructure is a compromise. So you have optimized the bimodal microstructure basically to have good optimum amounts of creep and fatigue. So this is a beta treated lamellar structure, and this is a bimodal structure. The bimodal structure is what is used for compressor sections, for making blades and other rings, etc., etc. Okay, so here I'm showing you why you want a bimodal kind of microstructure. Then about heat treatment, you have to be careful. You see, either the faster cooling rate after solution treatment or annealing treatment, or a slower cooling rate, both deteriorate the creep properties in all kinds of microstructure. That is, this is the temperature and stress applied, and this unfilled is for 40% primary alpha. These boxes are for 15% primary alpha, and this is for lamellar structure. The lamellar structure creep is best, but again, intermediate cooling gives you the best creep properties. This is for certain regions. I will again not go into too much of detail about this, but you have to remember that heat treatment plays a major role in all this optimizing the creep properties. Here I'm showing you the IMA834 rings that were made for compressor section of the Kaveri engine, for the Kaveri engine program. Okay. Billets were made, and then from that rings were made by ring rolling. And then blades, rods were made, and then it was forged gradually, and then these compressor blades were made of this high temperature IMA834. Now I will show you the effect of processing microstructure and also on dwell fatigue. This is an important new phenomena which is there, what is called dwell fatigue. I will tell you what is dwell fatigue. You have heard about fatigue, which is just cycling the load. But when you hold a load for a constant period of time at a higher load level, that is what is called a dwell period. And people have realized, because of this dwell effect, there have been cracks which have been generated, and there have been failures which have occurred in engines, and this has been reported. Okay, we will discuss about this phenomena because this is interesting phenomena. Now, in order to explain that phenomena, I am just showing you this critical resolved shear stress in a Ti6L crystal as a function of temperature. This shows you the stress required to move the dislocation. So here these are different slip. This is prism slip. This is for basal slip. I had shown you the hexagonal crystal structure, which if you remember. So this is prism slip, this is basal slip, slight difference, not much. Then the C plus A slip, as I had told you, there is a huge difference in stress requirement plus C plus A slip or pyramidal slip. So this is much higher. The stress requirement to cause this kind of slip or deformation is much higher. Why I'm talking about Ti6Al? Because this is the common unit on all high temperature titanium alloys. Okay. So that is why this is important. Now, what happens is, as compared to fatigue, as I told you, in dwell fatigue, you hold a load for certain amount of time at the highest stress, and then the crack forms. Now, there has been a explanation given by Bashe et al., which still hold good, but although a lot of research is going on in this, people have, and the other thing that is about dwell fatigue is that it causes an order of reduction in fatigue. I'll show you the exact values. And the other funny thing that happens is this dwell fatigue cracks initiate subsurface, not on the surface. We have been taught that the fatigue cracks initiate on the surface, but the dwell fatigue cracks initiate subsurface. Now, how does it happen? If you have differently oriented, that is micro-textured material, textured material, that is one has got different orientations. This is oriented for easy slip. I'm showing you this. I will explain you. Don't get worried. This is oriented. This region is oriented. Or this region of the material is oriented for easy deformation. That is why I showed you this. That is, it is oriented for prism or basal slip. The stress requirements are low. So this region is oriented for easy deformation, whereas there is a neighboring region which is oriented for difficult deformation. That is, it might, in that C plus A slip has to be activated. Other slip, critical resolved shear stress does not occur. So what happens is this deforms and unloads onto the hard oriented, not hardness wise, but deformation wise. And this adds, this stress adds on to the applied stress, and it causes fracture or cracking. That is how the dwell fatigue crack initiate. That is, adjacent oriented easy slip region deforms and unloads onto this, and this hard oriented region, the cracks. Now, if I take a stress strain curve and try to explain this phenomenon, it is like this. You have the hard oriented region and this region which is has lower stress requirement, and then there can be two cases. One is iso stress condition and one is iso strain condition. So if you take a iso stress condition, the weak grain deforms more as compared to the strong grain. So there is a strain incompatibility which comes in. Now, if you have this phenomena, if you have iso strain condition, the weak grain deforms and the strong grain deforms. So what happens is, when you apply these stress, the weak grain deforms and basically unloads onto the strong grains, and this is what is called load shedding or unloading, and it causes cracking in the hard oriented region. I will show you this. Now, for knowing the orientation, nowadays what you have is EBSD, electron backscatter diffraction. It is become very easy to know the orientation. Grain wise, you can focus and see what orientation it is, and you can get a orientation band. So this is an attachment to a SEM, scanning electron microscope. So this has got a camera, and when you orient your material properly, it can generate Kikuchi bands. These are from basically planes which are there in the crystal or your material, and these can be indexed. Very mathematical formulations are there. These can be automatically indexed and give you the orientation of each grain, how it is oriented. It becomes, so I will show you an example. And why we are talking about this, because we are bothered about the mechanical properties ultimately. Now, this is an example of how IMI 834 was indigenously produced in with DMRL technology. So it was triple melted 650 mm dia. It was upset forged in the beta phase field to 750 mm dia, then laterally forged in alpha plus beta field to get a 500 mm die at 450 mm dia billet. Then it was again beta treated and again alpha plus beta processed and got 250 mm die at 220 mm dia billets. This was used for making discs and rings. So what you see here is around 44% alpha plus beta reduction. Then this was further processed for making 25 mm dia rods for making blades, and it saw around 79% reduction in alpha plus beta processing. Now I will show you the difference. So this is another how you orient your material in the EBSD. You have to take care of your orientation. This is of the next study, part of my postdoctoral research. I will just show you this, but I'm showing you the orientation. Now this is from the IMI 834 that we had processed. You can see this is from a 25 mm dia rods that have been made, and this is from 250 mm dia forged billets. This microstructure is much finer, so it has seen a much higher alpha beta reduction. And orientation wise, there is difference, but you cannot pick it up here. So red means a hard orientation, that is its c-axis is oriented in the loading direction, and the green and blue means easy direction of orientation. And if you don't bother too much, I will just explain, because I'm coming to the mechanical properties. So these are basically maps which are made, and in 250 mm dia, these O02 poles are off axis as compared to the 25 mm dia is near the ND direction. And when you test these materials for continuous fatigue, this is how a sawtooth fatigue looks like as compared to the dwell with a dwell region. This is how 120-minute dwell around 0.95% of the yield strength. When you do that, this is the yield strength of both the materials. There is a slight difference because this is much finer material, so you get higher yield strength. And you can see the difference in number of cycles to continuous cycle. This type of cycle, this is around quite a large number of continuous cycle that is seeing, whereas this is showing much lower cycles to failure, continuous cycles. And similarly, if you see, you apply this dwell kind of cycle, this is showing this. So there is a debit, right? I mean, if you have a load period, although it is within the elastic regime, but you can see the decrease in life. So if you divide this number by this number, this is the number 4.5 NC by ND. So you get this. So you can, this is called a dwell debit. Now this happens at lower temperature, that is below 200 degrees centigrade. Now, if you see this, in this, the dwell debit is lower. But along with that, what you see is the fatigue life, both continuous as well as dwell cycle is much lower. Okay, so you can see the effect of processing, microtexture, and also the fatigue on fatigue life. Now then, this is a part of my postdoc work. I just wanted to show you the example. Ti6242 is the material which Americans use, and Ladish is the company which was producing this material. Now it was produced to give low microtexture material. This pancakes were produced to give high micro. I will show you all these examples. And then 2 were tested from beta forged condition, and they also checked from retired impellers. Now here they most of them were tested at around 95 to 91% of yield strength, and 2-minute dwell time was applied. And here you can see the continuous cycle and the dwell cycles, and the dwell debit is shown here. And you can see that the material which has got a higher microtexture shows higher dwell debit as compared to material which has got lower microtexture. And beta forged material, because it has got higher grain size and all, it shows lower debit and all, but still it has got higher not very good other properties also. And retired impeller again shows, which was processed much earlier than microtexture was understood, and in titanium alloys it shows very high debit, because that time the people did not understand microtexture properly. Now how these were processed? One was processed, alpha beta forging was done in T-50, that is for random microtexture. and then heat treated T beta minus 35 oil quench, and then heat treated. And then one which for higher microtexture, it was forged at T beta minus 50, but it was treated at much lower solution treatment temperature to have higher volume fraction, that is T beta minus 100, and then again air cooled and aged. Then beta forged again, it is a beta forged material which is processed in the beta condition, and then solution treated at T beta minus 35 and oil quench, and then again aged. Now these are the microstructure. This is a random one. This is the optical. I will show you the texture also, and then further on the SEM micro. This was alpha beta high for higher micro texture. For you can see the higher primary. This was beta forged, and this is again for another material which has got a different kind of micro texture, which I will try and. So this is pancake one. This is a randomized. You can see the color is very. There is no particular area where there is. You can see a micro texture or a dot of color. As compared to that, one which has got higher micro texture, you can see similarly oriented grains in certain region. This is called microtexture. In again macro zones, again in the Halimoil material also. So this let me show you the high microtexture material. So this is the microstructure, SEM microstructure. It has got a higher amount of primary alpha, around 70 and 30%, and so it was well tested. And these are the stress levels at this is 0.2% yield strength, 950 MPa, and this. So it was tested. Maximum load was 95% of. So this was tested on a flat sample, and you can see this flat sample micro radiography was done. This is the main crack, and these are fine secondary cracks which are there. It was imaged in two directions, and my job was to look for texture in the around the crack. This is a secondary crack which is there. So I polished up to the secondary crack and then took the EBSD map. You can see the this is the loading axis in the flat. I kept the track. So this is the loading, and this is the secondary crack which I'm showing you. So you can see the crack fully in the hard region, and as soon as it goes in the soft, that is blue and green color is soft, deformation wise soft region. It either meanders, that is it tries deviating, or it blunts. You can see here, and this is another material, and this fiducial markers were given because people had started doing crystal plasticity modeling, and they wanted serial sectioning of. So red means hard. So that is C axis is oriented in the loading axis. So there is no resolved shear stress on the basal plane or on the prismatic plane. Only the C plus A hard orientation can deform. So as I told, these deform soft and unloads onto the hard region, and these crack. So this is the phenomena, and you can see this is fully embedded. A crack is inside the material. It is not on the surface. And this is the main crack. Nowadays with EBSD and the SEM, you can see this is the flat specimen. The crack initiation region, which is the brittle region, is inside, not on the surface. And you can find out the physical orientation and also know the crystallographic orientation. It is possible nowadays. So you can do vector calculations, and you can Photoshop it. You can plug in into this. These formulas are there. These are just vector calculation, nothing else. I'm not going into too much of details. So you can calculate both the physical orientation and also the crystallographic orientation of the facet by pulling out a pattern. You can get a pattern from that from the faceted region, and then if you plot, it is the near basal region as Bashe had predicted. So these which are the crack initiation regions. Okay, so that is the hard orientation regions are the regions which start cracking. So that is what this study shows, as is shown also on the EBSD of the around the secondary crack. Even the if you analyze the primary crack also, the crack initiation region is around the hard orientation. Okay. Now, then we were given pieces of rings which were processed differently. And when we look at the macro, we etched it and wanted to see is there a difference in macro wise? There is a slight difference, but not too much. This is again different materials from differently processed rings. And and then these were ultrasonic attenuation was measured. Now, why we were doing this is because there is a lot of material flying around in US engines which were processed before microtexture was understood to affect these fatigue and dwell fatigue properties. So they wanted to assess non-destructively whether it is possible to pick out material with higher microtexture and material with lower microtexture, because material with lower microtexture is better as far as fatigue and dwell fatigue are concerned. So this was the different materials. We took the microstructure, looked at it in SEM, primary alpha, transform beta. There is a slight difference. These are different materials, sample 1, sample 3. This has got lower attenuation. This has got higher attenuation. This again, another sample, sample 2, sample 3, middle attenuation, and this is anomalous attenuation. So there is a difference in microstructure also. This transform beta region is more here as compared to this, but there is not a drastic difference. But when we do a microtexture scan, you can see that 4 process specimen are entirely different. You can see this specimen 1 has got very large regions of similarly oriented material. Specimen 2 also has got, whereas specimen 3 is got randomized orientation. Different grains are oriented differently, and this has got the orientation as stringers running from bottom to top. So ultrasonic signal was sent in this direction from left to right, and then what I did is I plotted the size of the microtexture region size in this direction versus attenuation, and then it plotted that is non-dimensional microtexture region size versus attenuation. If you plot, then it matches. That is the material which has got higher size of microtexture region, that also gives higher attenuation of ultrasonic signal. So that is how you can segregate the material without cutting. And this kind of material in which you have elongated grains, if you send the ultrasonic signal in this direction and from top to bottom, again the ultrasonic signal attenuation jumps. Okay, if you send signal in parallel direction to this, then attenuation is much higher, because this is showing higher microtexture region in this region. So you can segregate the material based on microtexture. That is, random microstructure, as I told you, will have lower higher fatigue life and higher dwell fatigue life. So that is better. So now I will switch over to another high temperature titanium material, that is gamma aluminides. I will show you why these are intermetallics. Okay. Now these have got very high amounts of aluminium of the order of more than 40 atom percent. All these compositions are in terms of atom percent rather than weight percent. They have aluminium in the range of 40 to 50 atom percent. So what happens is, when you add that much of aluminium, ordered structures start forming, and you get 2 kinds of ordering: Ti3L based ordering and TiAl based ordering. Ti3L is hexagonally ordered. Gamma TL is FCT ordered. It has got a different kind of ordering. So you get material, ordered material. Now they are, because you have added lot of aluminium, first thing that happens is it reduces the density. So it is for gamma aluminide, the density is around 3.9. So it's much as compared to normal titanium alloys. The density, the normal density is 4.5 grams centimeter cube. So you have the weight advantage here, and the elastic stiffness also increases. It is around 170 GPa as compared to near alpha titanium alloys, which have got 120 to 130 GPa elastic modulus. And it has got very good oxidation resistance, high tensile strength, and fatigue strength. And here I'm comparing the oxidation resistance of the third. There are different generations of gamma aluminides now. 4822, 48 Al2 chromium. This is a General Electric GE composition. It is very famous because the GE has fitted it in the flying engine and it is flying. Then there are GKS is again a German company, and then there are Plancy compositions, and the classification is based on niobium. If it is less than 5 atom percent, then it is second generation, higher up to 10 atom percent, third generation, and so on. So there is also a design criteria how you can decide what elements to add and all, slightly complex, but anyway, design is. So when you compare the oxidation resistance, you can see the near alpha titanium alloys have got poorer oxidation resistance. This is 800 degrees centigrade. In the second generation have got better, and third generation of gamma aluminides have got still better oxidation resistance. Here I'm showing you the properties why gamma aluminides are attractive, specific strength, that is in MPa versus density divided by density as a function of temperature. You can see it surpasses the near alpha titanium as well as iron 7 morty. It is here. Then specific modulus, much better as a function of temperature. Specific strength as a function of temperature, gamma aluminides are much better as compared to newer alloy steel. Also, the major issue is about ductility. You can see here gamma aluminides, the ductility is almost zero. Only above 600 degrees centigrade, it starts improving. So that also 1, 2, 3%. So the room temperature ductilities are very low, and so they have difficulty in processing. So we have also started some research on these. These are certain compositions. I'm not going into too much of detail. We can talk about. This is the GE composition which we have melted, and also other variation. People are going down in aluminium content, and they are adding in. And this is the oxidation resistance of these alloys as compared to the GE composition. This is our alloys have got much better oxidation resistance, and one node alloy has got very good keep resistance as compared to the GE composition also. So here is the phase diagram which I am talking about. So you have Ti3L based intermetallic. There was a lot of work done in DMRL on Ti3L based intermetallics. But the properties were not. Now people know that properties are not very attractive. But gamma aluminides, although very brittle, but it's got a lot of potential. So now people are doing a lot of research on these classes. So you can see the higher aluminum content, you get the gamma plus Ti3L bus. Now, so one of the ways of manufacturing is by investment casting. Here I'm just showing you the investment casting process. You first make the pattern molding, then assembly, then carry out the wax pattern you make, then slurry coat. You basically build up the slurry coating, build up different layers which are there, and then pour the metal, and then after that first dry the shell mold, and then pour the metal, and then break the shell mold, and then do different kinds of inspection to make a investment casting part. Why investment casting? Because these have got very low ductility, these gamma aluminides. So they are generally invested in cast. So this is the we are trying to make investment casting shell. So these are Y2O3 gel plus Al2O3 phase coat. So it is in the initial stages. We have kind of optimized the shell now. So here are the first few castings of the investment cast material. Here the microstructure I'm showing lamellar material, and then some of the newer gamma aluminides can also be wrought process, but at much higher temperature than 1150, 1200 degrees centigrade. Here processing map of a particular composition was studied, and then the region was identified where good microstructure can be obtained, because DRX, dynamic recrystallization, happens if you process in good region, and that is what we are trying to identify, whether we can also wrought form certain blades and all. So there is a lot of scope for research in these areas. Then coming toward the end, I will just come towards beta titanium alloys, which are high strength titanium alloys, mainly used for strength applications. Now, what are beta alloys? Beta alloys are basically alloys in which you have sufficient beta stabilizer content, and you can retain the beta phase by cooling at faster rates. And then when you age, you get very fine precipitation of alpha and thereby higher strength. So mind you, these are not for high temperature application, but these are for strength applications. So this is again, I'm pulling up the, I will give you examples from 10-3 and another alloy beta 21s, which are kind of located just beyond the martensitic formation line here. This is again so these are having sufficient beta. These alloys, he has got 10 vanadium, 2 iron. So you can see a lot of beta content in this. Also, you can see a lot of beta moly as well as niobium, etc. are there. Now, these are some of the examples of commercial beta titanium alloys. 5553 is one of the composition which is of interest to us because this can be used for making components with higher section size thickness. 10-3 we have just indigenously produced. It was there in the news. It is being used in the LCA and other aircraft programs for making several components of the aircraft to replace steels. So it has got corrosion resistance, and this 10-3 is well-established alloy abroad, but we have indigenously produced. And this is a beta 21. This is a sheet alloy, very good for sheet kind of application. And there are other compositions which are there. And you can see the beta transverse temperature of these alloys are much lower as compared to near alpha titanium alloys, which is normally around 1000 or more. So what are the application? High strength fasteners, helicopter rotors, aircraft landing gear. Because these beta alloys have also got lower modulus, so they can store energy, so are used for making springs, especially in aircrafts where price is not a problem. Then there are different aircraft structure. Then oil field application, especially in sour gas application. Then engine tail plugs. One of the alloys like beta 21s can be used, which has got a good oxidation resistance as well as good high temperature properties. Although beta alloys are not used, but this alloy has especially been designed with silicon addition. And then there is a whole class of alloys because they have lower modulus. They kind of match the bone modulus. So for orthopedic implants, etc., people are moving on from Ti-6-4 to these alloys. So this is, I'm showing you the aircraft structures, springs which are there. The beta alloys are widely used there. Then this is an example of 10-3 forging. You can see a person sitting this, one of the landing gears, part of the landing gear. This is the steel, but the other parts are made of 10-3, so it reduces the weight. Although the initial costs are higher, but because it has got corrosion resistance and all, it does not corrode, so lifetime costs are lower for these alloys. Now, here again, helicopter rotor mass rotors are also made of these kinds of 10-3 like alloys. Now, why they are attractive is because they have lower flow. Here I plotted the flow stress versus this from literature, I did not plot. 5553 versus Ti-6-4 as a function of temperature. You can see 10-3 has got one of the lowest flow stresses around the forging temperatures, and so it takes the shape of the die very easily. It flows very well at the forging temperatures. So that is why this beta alloy is very good for closed die forging process. Now we have indigenized 10-3, but I would just want to point out the problems that can be there. You have to have proper melting master alloys, etc. Otherwise, and proper melting technique. Otherwise, you'll end up with problem. Now we started off with 85 vanadium, 15 aluminum as used iron powder and aluminum shot, and a trickle melt was taken, 2.8 ton. That resulted in higher oxygen and also segregation of iron. These are called beta flakes. I will show you this. And then what we did is we used a different kind of master alloy, ternary master alloy, which reduced the iron powder addition. The oxygen was coming because of the iron powder, and we so only limited amount of iron powder was used, and we switched over from triple melt to double melt to reduce the beta flake problem. Size of the ingot was reduced, and melting from triple melting was reduced to lessen the beta flake problem. So that is how this problem was solved. I will try and explain the problem, beta flake problem. Now, the elements like chromium, copper, and iron, etc., have partitioning coefficient less than. What is a partitioning coefficient? Partitioning coefficient, suppose you have this alloy solidifying, and this is the phase diagram. Then this is the at this temperature, this is the composition of the solid that solidifies, and this is the composition of liquid which solidifies. Now, if you divide this composition by this composition, this is known as partition coefficient. Now, if this is less than 1, then what happens is, as you cool, because it's a solidification is a industrial solidification, let me put it that way, is a non-equilibrium phenomena. This type of alloying addition gets rejected in the liquid and it segregates. Now, this is the titanium iron phase diagram. You can see this is a deep eutectic which is there. So this is CS, this is Cl. So iron gets rejected into the liquid, and you have segregation of iron. In certain regions, you have preferential iron, and that causes problems. So this can be avoided by rapid solidification, smaller ingot, and ingot soaking. So here I'm showing you what is a beta flake. In this is a heat treated material. Again, I will show you another microstructure, and this is a scan for composition. You can see in this region there is a jump in iron composition. Okay, so this region has got higher iron composition as compared to this. So the beta transits of this region will be relatively lower as compared to this. Here again, I'm showing you the microstructure. Here, no beta flake, but whenever you have a beta flake, after thermomechanical processing, you can see this retained beta regions. You can see here. So you have big beta grains as compared to the other regions. So what happens is fatigue cracks normally start initiating there because of strength differential, and you have a problem. Now, why this happens is because when you heat treat at just below this transist is around 800 degrees centigrade, you have to heat treat around 780, 770 or so, because you also want good combination of fracture toughness also. If you do too much below, you will have too much of primary alpha and you will not get very good fracture toughness. So that also we optimize. So around this point, when you do the local region, that is this beta transist, as you saw, is lower as compared to the other region. So this crosses the beta transist temperature, and big beta grains you get as compared to the other region. So that is the problem if you have this beta flake problem. Okay. Now beta alloys, the problem is there is a because the temperature of processings are lower, you have to hit the right window for processing. Otherwise, you will get a non-uniform structure and you will not get good mechanical properties. So you have to hit the right window, because the temperature, strain rate, deformation, everything has to fall in place. So that is why processing these materials are not very easy. You have to hit the right window, and that you have to identify by doing research and processing and all, and that takes time. And here I'm just showing you the first heat treatment that we did in heat treat. We wanted high strength we got, but we got very low fracture toughness. So we modified the heat treatment, higher solution treatment and higher aging temperature, and we could increase, although we compromise on strength, which is okay, but we got good fracture toughness. And it is very easy to, as I told you, to improve fracture toughness in a beta treated material, but in a bimodal material, it is not very easy to increase the fracture toughness. And nonetheless, it was done by changing the solution treatment and aging temperature, because you are changing the primary alpha volume content, and thereby when you age, you are increasing the secondary alpha precipitation, and you can see the jump in fracture toughness which we could get. Here I am showing you the plot of different dias of the material, 60mm dia, 100mm dia, but I am not going into but that was also achieved by changing the heat treatment solution. Here I am showing you the microstructure. First heat treatment, you can see the higher amount of primary alpha, and this is very fine secondary alpha, which you can see in the second. So this heat treatment has got lower volume fraction of primary alpha, the dark colored, and coarser secondary alpha. This is what gives you strength. So this improves the fracture toughness. Here again, I'm showing you the TM pictures of these primary alpha and very fine secondary alpha, which you can see in TM only. And then when you do a different heat treatment at a higher aging temperature and higher solution treatment, you can see the coarser secondary alpha precipitation lats, and that is what improved the fracture toughness. And then we also are working on the development of the sheet alloy. This is much better than 1533, etc. This has got higher beta 21S, which has got good oxidation resistance and creep resistance. Although beta alloys are not supposed to have good creep resistance, but is comparable to Ti64. As you can see, tail plug, etc. of this material is used. So ADA wants to. So we had processed this alloy again with 85 moly 15 aluminium, and we could process it to 0.8 mm thickness in the lab. There was no issue, and we did property evaluation in solution treated as well as solution treated and age condition, both at room temperature and a higher temperature, and we were getting good property. This I'm showing you the age microstructure at different aging temperature and beta treated single phase microstructure. You want these sheet material to be in beta treated form because, for forming certain component. After you form, you can age it after forming the final component to gain strength. So then, but when we started melting on industrial scale, we did not get that 85 moly 15 aluminum master. So we had to go for this master alloy, which was only available 65 moly 35, and we had to use lot of moly powder. And this ingot was processed to 12 mm thick, and then we started getting ultrasonic signal of defects. When he cut and see, we could see unmelted moly surviving the even 2 VAR melts. So moly did not melt. So what we did is we moly is not known to segregate because it's got a isomorphous phase diagram. It is not like iron. So the problem here is reverse of that of iron. So what we did is we changed the melting procedure. So we melted at higher melt rate, and we change it to triple melting, so that our melting pool, melt pool was there for longer time, and so that moly could dissolve. And then the other problem was on the sheet, when you heat treat, because we don't have, you start forming oxide layers which look like this. So that you have to remove by proper procedure, which was removed. Again, your single phase material beta treated, so that is why you are not seeing any contrast. So this is the deeply etched condition, optical. You can see big beta grains which are there. This is the condition in which it is to be supplied, because it is to be. Then when you age, you get very fine precipitation, big beta grain, very fine precipitation of alpha. That gives strength. Okay, so this is sheets are made, bend test, cup test, except for sheet applications were done to check the material, and it turned out. The other alloy that we are working on is 5553. This has got higher hardenability as compared to 10-3. This is required for higher section size thickness for making bigger components. So we had done a lot of lab scale studies, both in beta treated condition and alpha plus beta deformed solution treated in age condition. And this is how it was processed, ingot in beta regime, then alpha beta process, then both solutionizing in different temperature and aging at different temperature. These are the different microstructures which we generated, and we generated a lot of mechanical property data, and alpha plus beta treated material showed good combination of strength versus elongation. So we are now going in for industrial scale melting and processing for program of ADA. So I will briefly talk about biomedical application, and I'm coming towards the end of my talk and also the time. just 2-3 minutes, I'll finish. So biomedical alloys are again of interest. India does not make these. Now we have started. For most of the biomedical application, we still use Ti6-4. Right, Ti6-4 has got several problems. It has got cytotoxicity. It has got higher modulus of elasticity as compared to bone. Bone modulus is around 40-50 GPa, 30 to 50 GPa, and this modulus is around 130-120 GPa, so much higher. So there is a problem of load shedding, etc. So, and then biocompatibility, and then allergic reactions. What is cytotoxicity? This vanadium in Ti6-4 is suspected to promote cancer. Therefore, over a period of time, vanadium was replaced by iron and now niobium. So these are the newer generation alloys which have come up. Still, these are still old. There are still other aluminium alloys that have come up. Aluminium also was suspected to promote neurological problems. So aluminium also have been replaced in titanium alloys. Now, some studies are going on, but not much in DMRL. But there are other places where it is going on. So as you can see, the different material, the elastic modulus is plotted. Copper. These are all biomedical alloys which are there. 316 stainless steel. Bone is here, and this is PMMA bone material. MB polyethylene, which is again used for biomedical application. And so titanium alloys, new titanium alloys have got much lower modulus and thereby much more compatible with bone structure. And this is again another, this has got newer titanium alloy 35 NB. So this is completely a beta alloy, as you can see, and has got although still would like to go this side, still lower, but there are studies which are on. So but it is much lower as compared to other biomedical material which we had earlier. So there are ways to design this. The material which twins, that is forms twins, have got lower modulus as compared to material which deforms by slip and all. So people are aiming at that kind of composition, etc. So there are certain ways to design these alloys. So newer compositions are coming up, which will probably, here again certain, I will just showing you the comparison of the elastic modulus of CP titanium, Ti6L 7B, which is near Ti6L 4B, yield strength, percentage elongation. You can see the basically these newer alloys have got much lower modulus. Here I'm showing you the different, again, this work was done in quite some time back in DMRL. Hip joint, there can be different kinds of design. Again, it has got pros and cons of designs, etc. But titanium alloys are very much in the offing for implants also. There is a big industry which is there. Thank you. Here is the picture of a latest GE Gen X engine, which in the last two sections uses gamma aluminide, which is quite brittle. It's like ceramic, but their engineering allows them to use these kinds of brittle materials also. And this is flying in a commercial aircraft. Thank you very much. If you have any questions.
Thank you, sir. Thank you for covering a wide variety of titanium alloys, sir. Thank you for this informative session, sir. Participants, if you have any questions, you can please unmute yourself and ask, sir. Or you can even type it in the chat box.